Hi everyone, welcome to the Temporal Graph Reading Group today. We are very glad to host Veronica Lachi from the Mobile and Social Computing Lab at Bruno Kessler Foundation. And Veronica is a researcher in the Mobile and Social Lab at the Bruno Kessler Foundation in Toronto, and her research interests focus on theoretical properties of GNNs, particularly their expressiveness, hierarchical pooling, and temporal GNNs. She obtained her PhD in AI from the University of Siena under the supervision of Prof. Monica Bianchini. And during her PhD, she was a visiting researcher at UIT, the Arctic University of Tromsø. And yeah, so we're looking forward to your talk. And congrats on getting your PhD. I remember when you had the first talk, you were still a PhD student, or did I
Yeah,
remember
yeah,
it
it was.
incorrect?
Yeah, I think it was almost 1 year ago, and I was still a PhD student. So now I finished, and yeah,
Yeah,
I'm a postdoc now. Yeah,
congrats. Yeah.
thank you very much.
Okay, so I'll hand the mic to you. Yeah.
Okay, hi everyone, and first of all, thank you to the organizer for having invited me here today. And so let me share the screen. Can you see the screen?
Yes.
Okay. So today I would like to present this work, which is titled Boosting Relational Deep Learning with Pretrained Tabular Models. And this work has been done in collaboration with Antonio Longa, Beatrice Bevilacqua, Bruno Lepri, Andrea Passerini, and Bruno Ribeiro. So the first aim of our work was that of proposing an efficient way of learning on relational databases using graph neural network learning and knowledge distillation. So first of all, what is a relational database? A relational database is a collection of tables connected through primary and foreign keys relationship. So relational databases are widely used in industry as they are very efficient and they can be easily accessed through SQL. So a lot of these companies use this way of storage data. And so one example of relational databases is the H&M relational databases from benchmark, which is a benchmark for relational deep learning, which has recently proposed. So in order to understand better how relational databases work before going into the details of the machine learning method for that, I would like just to explain a little bit better this example in order to understand better the relational databases. So the relational databases of H&M consist of 3 tables. The first table is the article 1, where you have all the information about the article that can be sold into the e-commerce platform of H&M. The second table is the customer 1, where you have all the information about customers that are registered to the e-commerce platform. The third table is the transaction 1, where you have information about which customer bought which articles. So as I was saying before, the tables into our relational databases are connected through primary and foreign key relationship. So first of all, what is a primary key? So a primary key is a special column of a table that uniquely define each record in the table. So for example, the article ID is a primary key for the article tables because every row is unique. So every ID of the article uniquely identify the article which can be sold in the e-commerce platform. Instead, the foreign keys are other particular kind of columns that reference to the primary key of other tables. So for example, the article ID in the transaction table is a foreign key column because it references to the article ID column of the article table. The same can be said for the customer ID column. So the customer ID is a primary key for the customer table, while it is a foreign key for the transaction table. So in this case, we have that we can connect tables using this relationship. So far we have talked about primaries and foreign keys, which are particular kind of columns, but there are some other columns which are the feature of the tables. And in particular, there can be categorical features, like, for example, the category of an article, or also numerical feature, like, for example, the age or the price of a certain transaction, and so on. And what is really important is that there is another special kind of features, which is the time step, which is particularly important because, as we will see later, it makes handling and addressing the task on relational databases particularly difficult, and it is important to have an appropriate design of the model in order to deal with the time step that we have in the relational database. So, since, as I was saying before, companies heavily rely on these relational databases, there are interesting learning tasks that can be addressed on relational databases, which are of particular interest for companies. Like, for example, one company can be interested in predicting the future state of entity into the entities of the relational databases. So, for example, one company can be interested in knowing how much will the total sales for one particular article be in the next week. And this is an example of regression task on relational databases. Or, for example, an industry can be interested in knowing whether a customer will churn or not in the next week. And this is an example of classification task. Of course, there are other interesting tasks which are not at an entity level, but a relationship level. And these tasks are commonly used for recommender systems. So, for example, companies are really interested in knowing which articles will a customer purchase in the next week, for example. So in this work, we concentrated on the first kind of tasks, so entity level tasks. And it is very important to highlight that these tasks are related to one seed time. So all of these important questions for companies basically have a seed time, so a time where you want to have the prediction. And this will be important, as we will see, because it is important for the design of the model.
Quick
yeah.
question on the tasks. So here, basically, the entity level tasks are no level tasks for temporal graph, and the relationship level tasks are edge level tasks.
Exactly, yes. Yes, so far I didn't speak about graph because I still have to show you how we transform these on graph, but basically, as we will see later, these entity level tasks will be transformed into tasks on a node level based, and while for relational level tasks are edge, like link prediction, basically.
But technically, like, it's less explored in the literature, but there's also like subgraph level tasks. Like, you can say all the articles in this category, what are the total sales?
Yeah, of course.
Or something like that.
Yeah, I think that this can be a really interesting task. So for this work, we concentrate on the RealBench benchmark, which is new release, and it's quite a very important like benchmark for relational databases. And so far on this benchmark, there are no tasks of this type, like subgraph entity, subgraph level tasks. But for sure, yes, I also agree that there can be also interesting studies on this. So maybe as future work, this can be, of course, interesting.
Sounds good. Yeah, thanks.
Thank you. And so, in order to address these tasks, machine learning methods must handle, first of all, relationship between entities, as I was saying before, foreign key and primary key relationship, basically. The temporality, because there is this special feature, which is the time step, and the heterogeneity of the features, because there are, as I was saying, categorical, numerical, and so on features. There are two main categories of machine learning method that have been used for solving this task. First of all, tabular methods, and in particular, gradient boosting decision method. So like XGBoost or like GBM, where you have a weak decision tree, which are ordered sequentially, and each weak decision tree correct the error of the previous one. And then, especially recently, relational GNNs. So, and the most important method in this framework is the RDL method, proposed together with the RealBench framework. So in this case, as I was anticipating before, we can transform the relational databases into a graph. And this graph is somehow heterogeneous because we have different kind of nodes, and also temporal because, as I was saying before, there is this special feature. So in order to properly use a GNN on this kind of graph, you have to handle both temporality and also heterogeneity of the graph. So these are the two main families of method used so far. I just want to explain briefly both the main characteristic of the two methods. So starting from the tabular methods, as I was saying, in a relational databases, you have more than one tables. So first of all, if you want to apply a tabular method, you have to create one unique tables starting from the collection of tables. And this is usually made by a domain expert. And this is the so-called feature engineering step. So this domain expert looks at the table and understands which feature can be crafted, created in order to aggregate the information of the 3 or 4 tables that you have in the relational databases. And so basically in these ways, you can use also some kind of, for example, rolling statistics and so on in order to aggregate temporally the features that you find in the original relational databases. Once you have one unique table, so with this feature engineering produced, you can apply a tabular method like XGBoost or like GBM. And so in order to answer to a question related to a learning task, you just perform a prediction with the tabular methods and you obtain the answer that you want. In the relational deep learning, so RDL instead, also in this case, you start from relational databases and you want to create one graph. And they call this graph relational graph. And in particular, this relational graph is up to time t, in a sense that we can start from the learning task. As I was saying, in each learning task, there is one seed time. And they construct a graph considering all the interaction and the entities before the seed time. So if the seed time is next week, we can take the relational deep learn, the relational databases up to time next week. So basically, every entity in the relational database is a node, and the edge between nodes represents the relationship produced by the foreign and the primary keys relationship. So, for example, we start with this customer. This customer in the first week bought this article, and so we have this part of the graph. Then at the second week, we have other customers that bought other articles, and so on up to time t. So as you can imagine, this graph is huge. So if you think, for example, at e-commerce platform like H&M or also Amazon, which is in the RelBench framework, these kind of transactions are at very seconds level. So this graph is very, very big with a lot of users, a lot of transactions, and a lot of articles. So how do they use the relational graph? So basically they took all this graph up to time t, and they used an heterogeneous GNN on this graph in order to produce a prediction on a certain node for the seed time. This is how relational deep learning work and also how tabular methods work. Can we compare the two? Yeah.
Can I ask a quick question on the previous slide?
Yeah.
So on this graph here at the bottom, would there be, so all of the features that you have in each of your relational tables, would they go as node features, or would you incorporate them into edge features?
No,
somehow?
They are all on the, so all the features of the entities are on the, as you see, it's a little bit weird in a sense, because also the transaction table that you can imagine that the transaction is an edge. Instead, no, the transaction is a node itself. And so all the rows of every table is a node, and all the features of the node, of the rows will be a feature of the node. You can use several ways to encode these features, and then I will show also how we decide to encode all these features in the node. But yeah, they are featured on the node.
So there's no information in these edges other than that they're connected. Yeah,
exactly.
Okay, cool. Thank you.
You're welcome. So I was saying we can compare the two methods. In particular, we report here the comparison between light GBM and RDL. So we choose as tabular method light GBM. We can see that, so here you can see tasks taken from the RelBench framework, as I was saying before. So you can see that these the first names are the data set, and then you have several tasks. And we have both regression tasks, which are the first block of the tables, and classification tasks, which are the second block of the table. And if you compare the performances of tabular methods and RDL methods on several tasks, you can see that the performances are more or less comparable. So there is no method that win always on the other, basically. But there is an important thing to highlight is that RDL is on average 57 times slower than light GBM. So in order to construct all the graph and to process the graph that is very big, the RDL requires a lot of time. So basically this makes us asking some questions, research questions. So first of all, is it possible to optimize the use of temporal relational graph neural network on the relational databases in order to mitigate the computational overhead? And second, is it possible to combine the two methods in such a way that we can achieve good performances, but also have a computational efficiency? In order to answer to these questions, we propose our method, which is called RDL, which is based on two fundamental steps. The first one is the construction of a more efficient relational graph. And the second one is the use of tabular model distillation in order to handle the temporal information of the relational databases. So let's start from the first part, so the construction of a more efficient relational graph. So just to recall, this is the relational graph up to time t of RDL with all the interaction from the beginning to the last week or month or day before the seed time. So as I was saying, this graph is very huge. And so intuitively, the first way of having a, let's say, smaller and sparser graph is that of considering, instead of all the interaction up to time t, just the last interaction. So the interaction of the time immediately before the seed time. So in this case, we have what we call the snapshot relational graph. So the snapshot, the relational graph, instead of considering all the iterations up to time t, consider just interaction at time t, okay? So of course you can say, okay, but in this case, you lose a lot of temporal information of what happened before. But our claim is that we can encode the temporal information on node features instead of using all the interaction of the graph that makes the graph very, very big. So our aim is that of using the information learned by the tabular models and use this information as node feature in order to have the temporal information encoded in the node. So the second step is the tabular model distillation. So what happened in a tabular model, as I was saying before, you have these tables, and in this table, there is all these feature engineered, all these features, which contains the temporal informations, because these tables is produced by the aggregation of all the table in with all the time step. So when a tabular method is trained on these tables, it learns some prediction, it has some output, and we claim that the tabular method is able to learn the temporal information. So inside the knowledge learned from the tabular method, there is the time information. So what we did is use an MLP in order to distill this information. So we used a two-task add MLP. And the first task add is trained on the dataset with the correct label, while the second add of the MLP is trained with the dataset with as a label the prediction produced by the tabular methods. So in this way, the MLP is trained to learn not only the dependencies between the data and the actual label, but also the knowledge learned from the tabular methods, which we know from literature that they are very good in learning the information of the table. So we use two different laws for the two tasks, and what we did is we take the representation produced by the last hidden layer of the MLP, and we use this representation as an embedding containing all the information about what happened before time t. And so we use this feature as an additional node features on the graph. So basically we have our snapshot relational graph, which contains just the interaction of time t. And then we use this embedding produced by this MLP, which is trained through knowledge distillation, as additional node feature on the node on which we want to have the prediction. Also, in this case, we use an heterogeneous CNN and we obtain the prediction. So what we get with this method? So we test our method on the same RailBench tasks and data set of RailBench. And as you can see, so also in this case, we have the first block is regression and the second block is classification. So we have that our performances are better with respect to light GBM, so plus 3.9 of in regression and plus 1.8% on classification with respect to light GBM. With respect to light RDL, with respect to RDL, we have plus 9.5, plus 1.7. So in both classification and regression, we have better performances with respect to both light GBM and RDL. What can we say about time? So what we claim at the beginning is that we wanted to be more efficient with respect to RDL. So we wanted to propose a method that is GNN based and that use the temporality in another way, and this other way is more efficient. So we can see that our method, light RDL, is 2 times faster than light GBM and 159 times faster with respect to RDL in regression, and 3.6 faster and 101 faster than light GBM and RDL in classification tasks. So there are a real improvement on the time, on the speed of the model. So let's
just a quick question.
Yeah.
How come you are faster than light GBM? Don't you use it in your model, if I understand correctly?
Yeah, okay. Here we consider just the part of the inference, basically. So the inference, when our model do the inference, it's faster, but I will explain it better, this summation, in the next slide. So here I will show how we calculate this time.
Okay.
So for inference time, so for calculating the inference time or our method, so the red one, we sum the time of training our GNN, which is the red time, plus the time for the distillation. So inside so for the inference time, we consider both the distillation time, so the time of the inference of the distillation, and the inference of our method. And so you can see that, so summing these times is still faster than the complete RDL. And we arrive to be also 526 times faster with respect to RDL. For the training time, we consider instead both. So in order to calculate the training time of our method, we sum the training time of the light GBM, the training time of the distillation, and the training time of our GNN. And so even in this case, we arrive to be at a maximum 72 times faster with respect to RDL. We consider also the time that the time that it is taken to construct the relational graph, because as I was saying before, in order to construct a graph, we have to start from the relational databases and construct the relational graph. And we are twice faster because, of course, we use a smaller graph. And so in order to pass from the relational databases to the relational graph, we are twice faster. So basically, our method is more efficient both in constructing graph, in training, and also in inference.
Yeah. It's still confusing to me. How are you faster than the light GBM?
Okay, in this, in this, so here in this time, we consider just the inference of our method. So we don't sum. I see your point that you are saying if you use
yeah, how are you faster?
You
yeah, exactly.
Yeah, so here we just consider the inference time. So the inference time of our model is just the inference that
so the GNN forward pass and
yes,
MLP forward pass.
Exactly. Yeah.
Yeah,
so
I think this is confusing. Yeah.
Yeah, okay, so you suggest here not to show this kind of,
Yeah, I don't think you should be. Yeah, you can say that. Okay, you are about. Yeah, you are like the overhead on top of like GBM is minimal, but
yeah, okay, yeah, I see.
yeah, because you still need to run it, right? You still need
Sorry,
to
what?
run. You still need to run the light GBM for inference, or
Yeah,
you don't
okay.
need to run it.
So we're supposed to have the large GBM trained with the, so let's say that our base hypothesis is that the industry and companies have this feature engineering ready with all these data ready for use, okay, to be used. So in a sense, it's like you take these prediction already given from industry that have produced this.
And you have also distilled the GBM into a multi-layer perceptron, right?
Yeah.
Okay, so at inference time, you don't actually run light GBM.
Yeah, okay, yeah.
Okay.
Yeah, I see your point.
Exactly. Basically,
Yeah.
exactly.
Ah,
Basically, at inference time, you use, instead of using the light GBM to make prediction, you use the distilled model to make the prediction. And then you are using the embedding, like computed by this MLP used for the distillation, as additional feature for the GNN. And this is why the light, this is why our model is faster with respect to light GBM, because light GBM in inference, because light GBM has been used for training and for training the distillation. But once the model
Okay.
has been distilled, it's just a matter of passing the new instance through the MLP and then
I
use
see,
them.
I see. Because, okay, you basically build the MLP becomes a surrogate function for the light
Exactly.
GBM.
Yeah.
Okay, so now it makes sense to me because otherwise I
okay.
thought you need to compute the light GBM and then feed it to MLP and then you get something else. Okay.
No. It's
Okay, so this makes sense. Yeah.
Thank you, Antonio.
uh,
Okay,
sorry.
so I was here. Okay, so time. Okay. So now some ablation study. So first of all, we ask ourselves if the temporal information is really necessary. So basically, can we avoid to put the temporal information on the snapshotted relational graph? And the answer is no. So we try two different models. First of all, we tried light RDL without the time information. So basically, this is just an heterogeneous graph neural network on the snapshotted temporal, on the snapshot graph. And if you compare this method with our RDL, we see that RDL is better in most of the tasks. So the answer is yes. Second question is the distillation essential? So can we just use the prediction of light GBM as additional node feature instead of distilling the information of the light GBM into the MLP and taking the embedding? So in order to answer to this question, we try this other method, which is light RDL with prediction. So basically here we have the snapshot graph and we put as additional node feature, not the embedding, but just the prediction produced by the light GBM. And also in this case, we have that in most cases RDL wins. So also for this question, the answer is yes. Another question is, can instead of using the embedding or the prediction, use the feature engineered produced by the domain expert directly on the graph? So we have that this domain expert is able to produce these very strong features. So can we put these features on the node of the graph instead of using this distillation and so on? And the answer is no. So we tried to put this feature engineered directly on the graph, and the performances are worse with respect to light RDL. And this is because probably these features are very good for tabular methods like XGBoost, like GBM and so on, but they are not explicitly made for graph neural networks. So the problem is that these features are designed for work well with tabular methods and not for graph neural networks. Last question is, can we try to make these time windows bigger smaller. So how the performances of our model change if we consider the snapshot graph smaller or bigger. So we try different time windows, and we see that the performances are close, so within the standard deviation, let's say. And so we can say that our method is robust to the choice of time windows. Of course, if you choose a time window that is very big, you became more similar to the original RDL and so less efficient. So of course, the performances are kind of robust, but you lose in terms of speed up with respect to RDL. So in order to conclude, we propose this method, light RDL, which combine tabular methods, which are able to handle the temporal modeling, and relational graph neural network, which are able to handle the relationship between entities. How do we combine this method? We combine this method through knowledge distillation. And what we get is a method that is up to 33% faster performance improvement with respect to the RDL method, and also up to 526 times faster in inference with respect to RDL method, which is quite important, especially for industry application, because it is very important to have very low inference time. So thank you very much. Here you can find the QR code to the archive and also the GitHub with the code. And if you have any other question, you can ask me now or also later. Thank you.
Yeah, thank you for the great talk. And that was very clear and very interesting work.
Thank you very much.
So I have more questions, but if there's any question from the audience, feel free to type in the chat or speak now.
Yes, I have a question. Could you please go back to the distillation slide with the loss, because that went a bit fast.
Sorry, I went in time. Okay, can you see? No, you cannot see the screen. Now, can you see the screen?
Yes. Yes. I think it was.
No, sorry.
Further down. Oh yeah. Yes.
Okay.
Exactly. So I just wanted to understand this, right? So if we stay in the tabular world for a bit, you basically have your data to the right, and then you have your predictions to your data to the left and your predictions to the right.
Yeah.
And then how was it that you trained your MLP? Did you put both the left table and the right table in as features, and then you train towards what, or kind of what goes in and what are you training it with?
Yeah, so I can imagine that this is a little bit confusing. So suppose that you have, maybe I have to change this slide using two right columns. So suppose that we have two targets, the actual one, which are the supervision that we have, okay? And this is one kind of target. Then you have another target, another label, which is the prediction produced by the light GBM methods, okay? And so suppose that we have two datasets, two different datasets. So the data on which you train your MLP is the left table. And then the target in one dataset is the actual value that you want to predict. So the one that you used in the light GBM to train the light GBM. And in the second dataset, you have the table and the target that you want to predict. So the ground truth is not the real ground truth, but is the prediction produced by the light GBM. Okay. So is it clear so far? Just imagine these two datasets.
Yes, sort of.
Yeah, okay. Then you have the MLP is a two-task-head MLP. So you can think of training parallelly. So in the same time, this MLP with these two different datasets, and you have two different laws. So they are the loss, which is the loss with respect to the correct label of the data, and the soft loss, which is the loss with respect to the prediction produced by the light GBM. You combine these two losses and you train the MLP. So basically, it's like you have the light GBM is a sort of teacher. So you have the reality, so the data set that you know that is real with your target. And then you have a teacher model, which is the light GBM. And the MLP is a student model that must learn at the same time from the reality, so the data set with the actual label, and from what light GBM has learned before.
Okay, so if I'm to understand it correctly, if we take a look at the data that you here have on the screen, right? Then you have a label. That's the first column. That's the ground truth.
Yes, right. Yes.
Mm-hmm. And then if we skip article ID, then you have like color, weight, average price, and so on and so forth. Those are like input features.
Yes, right, exactly. Maybe I have to separate like the label with the rest with respect to the rest of the table. Yes.
Yeah, exactly. And then your output is two predictions. So on one hand, you're trying to predict the label that goes into the hard loss, and then on the other hand, you try to predict the prediction of the tabular method, and that kind of goes into the soft loss, right?
Yes, right. Yes.
Okay.
And this is because, sorry.
No. My second question is kind of an extension of this, but go ahead.
No, I just wanted to say that this is because tabular methods are supposed to be better with respect to a standard MLP. So a standard MLP with just the label and the table is not able to learn properly. Indeed, instead, if you use also the information that the tabular methods has learned, it's easier for the MLP to learn the correct information, basically.
Okay. I think that was that makes sense, and then that also answers my second question.
Okay.
So but I think having this figure kind of like what goes into the hard loss, what kind of goes into the.
Yeah. I have
this was very cool.
Yeah, to structure better this slide.
Oh no!
I know that this is, I think, the most difficult part of to understand of everything. So you can think that usually this distillation is used on the other way around. So normally is used for explanation. So for example, if you have an MLP, you are not able to give the decision of the MLP are not explainable. So you can distill the knowledge learned by the MLP into a explainable model. So maybe the explainable model is in some cases less powerful than the MLP, but it can give you some explanation of the decision. So usually distillation is used for something like this, or yes, this is one example. So in this case, we wanted to use a distillation in order to extract an embedding, because with the XGBoost, we are not able to have an embedding. We can just have the prediction, because XGBoost is a black box model where you don't have embedding of the latent representation. But we wanted a latent representation, and so we distill the knowledge learned from the XGBoost into an MLP in order to being able of getting one latent representation, and moreover, this latent representation have some information about the temporality, because tabular methods learned the temporality, basically.
And I think that was kind of along the lines of my second question, that did you also just try to use like XGBoost's prediction as a node feature rather than distilling and taking the embeddings?
Yes, it was this ablation study here. So the second one, is distillation essential? So basically in this method, light RDL with prediction. So this is just the snapshot graph with the prediction of the XGBoost without the distillation. And as you can see, the performances are lower with respect to the one by the light RDL. So in a sense, this ablation study tells us that the information contained into the embedding is richer with respect to the information contained just into the prediction, basically.
Okay. Cool. Thank you. I yield my time.
Sorry, what?
No, I yield my time. That was my way of saying I don't have any more questions.
Thank you. Thank you very much.
Yeah, and thank you for the question. That was quite interesting. It's still a little bit counterintuitive to me why directly learning the label give you a worse performance. Because why you still need a soft loss when you just have the hard loss and that's the correct label. So maybe that's some sort of learning. Yeah.
Yeah. So yeah, it's like it's a sort of so it's one information more. So the information that is learned through the XGBoost model
It's kind of
can,
like regularization in a sense. Maybe. I'm not sure.
yeah, it can be also thought about something like that. Yes. Yes, so there are some studies on also this powerful of distillation in this case. So there is this paper of Hinton where you can find some like a sort of intuition about how distilling this stuff can work better than just taking the the information of the actual label basically.
And what if you, instead of MLP, you just use a GNN for this still? You still have the
Yeah.
soft locks with the tabular methods, but now you are using a GNN, which the output head is still an MLP. But then does it just skip over this MLP you need to train?
Sorry, what? I didn't understand the question. Last question.
So basically, if you, instead of this two task head MLP, you just use the GNN here. And the GNN, the GNN takes input the graph, and you distill the soft loss from the tabular method. Would that boost performance?
Okay, we didn't try this. I think that this can be another interesting question, so maybe we can also try. We didn't do this kind of ablation yet, yeah. But yeah, I see that this can be of interest, I think, yeah.
And I guess this could also be similar to adding an MLP layer before you add the GNN layers, right? So that you kind of learn the whole thing.
Yeah, so far it's like not Antonio, if you want to say something, yeah.
Maybe I would like to, regarding the previous question, maybe I would like to add a few words. I think that our intuition to distill and the fact that distillation was better than point-wise prediction was that in the ideal situation in which light GBM was not a black box model, so that you can use derivative of the point instead of the prediction. And our intuition was that instead of giving a single point, allowing for have a surface which bring much more information instead of the point-wise prediction. And this is, I think, is what motivated us to say, okay, it's a black box model. We do not have derivatives. Okay, there are techniques to compute derivative of black box models, and there is a line of research in that direction. But we thought that an easier way is to, okay, let's start distilling it and taking the embedding, because there are studies showing that the latent representation of MLP is comparable with the derivative of a black box model if the distillation is perfect.
I see. So
And
the MLP is approximating the derivative of the tabular method. So that's what you wanted to do. Okay.
Yeah.
And regarding the idea of using the GNN, I think it will be really interesting. But what I'm what I think could lead to a problem is that we tried an experiment that Veronica showed before, in which we use the GNN with the actual features, the feature engineering. So we have our GNN, adding to this GNN the feature engineering, but the GNN was not able to capture meaningful information through this embedding, through the actual, because, okay, sorry, let me repeat it. if we suppose that our GNN is a gene in which we have an MLP on the feature, then basically we are doing the same procedure, but in an end-to-end manner, right? And it's kind of what's happening here in this RDL without time with feature engineering, because we fed directly engineered features on the node into the GNN, and thus, since we could try with a gene, you are applying an MLP on the feature and then propagating the messages. But we find out that this was not converging. And to be fair, I don't know why it did not converges, but it could be something to better investigate. Thank you a lot for the comment.
Yeah, thanks. Yeah, I think that makes sense. So without time here means you do not have time information, right? So if you still have the time information here, then maybe it will boost its performance. But like without time is then you don't have the MLP part, the surrogate.
Yeah.
Okay.
Yeah.
I see. Okay.
There, it's something definitely to try. Thanks for the suggestion. Yeah.
You could also try, there's also like recent work, I think, starting to try transformers on RDL task. So that's also a different alternative.
Yeah. Yeah, I think that the underlying idea of this work was to, from one side, boost what companies already have, that is feature engineering, and on the other let's say, side, it's kind of combining, in some sense, orthogonal models. Because we don't have this in the paper because it's something that I do believe needs more reasoning. But I have the feeling that these tabular models learn something different of what a GNN can learn. So in some sense, I can see those models as incomparable, and thus we believe that combining them together may lead to a stronger model capturing both positive sides. Of course, we did not prove it in the paper because it's just, a thought we had. And I think much more research is needed to formally prove this. But
that makes sense. But also GNNs have their issues. So maybe it's not that GNN are not expressive enough. It's more like how learnable is this table when you have so many entries and you have like over smoothing and all these things. So this could be part of the reason.
Definitely.
And a second question that I have, I find the work very interesting. So basically your efficiency gain, as you show in the table, depends on your discretization level, basically. How much you discretize time. So I see that you push to like 13 days or something in the other table, but I wonder how far can you push it and how's the performance changing? Because I think this also is an understudied area in temporal graph where you're looking at different task granularity and I guess fundamentally you want a model that can give you consistent predictions across different time granularity. Like for example, you want to predict customer behavior and you want both like weekly forecasts and monthly forecasts. So does it mean that you have to train two separate models? And then does it mean that they are independent? Like it's not good they are independent because the weekly model could fluctuate a lot while the monthly one is pretty stable. So then so then there's no consistency between the two, right? And then when you're making a decision, you need to kind of choose, okay, which one do I prioritize and, how do I understand this information? So I think this also like one interesting direction here that you see that, you have more efficiency on this and, what's the actual information that you need to keep for the best prediction because you get rid of all the past history, basically. That's kind of where the most efficiency come from, right? From the GNN side. The graph gets smaller, right?
Yeah. Indeed, actually, this was like in this table, I just reported the performances, but I didn't report the time. We have them in the paper. So, of course, if you make these time windows bigger, then you are going to lose the efficiency because you are going to be more similar to the standard RDL framework, of course.
Yeah.
Yeah, but we have to say that from this analysis, of course, for this case, it's like a sort of preliminary analysis because we have just the driver data set and not all the data sets. So this is one thing on which we want to also investigate more. But you can see that even changing these time windows, of course, you are less efficient, but it seems that the performances are still good, meaning that in some way, entering this temporal information with this distillation seems to be quite robust. So even if you change the time window, then the amount of information is just changing from the graph to the embedding, but the performance is still remaining good. So this is, I think, a good point that we still have to investigate more, maybe using all the tasks. And so we decided, so for the result that I showed you before with the bar plot, in this case, we decided to take the time window in such a way that the time window for the validation was the same. So we choose the time windows as the time window in the validation, since we use this real benchmark. So we started from this, but then we also try to make this bigger. Of course, making this shorter than 13 days, for example, can lead to some problem because the graph became very sparse, and in some data set, for example, we didn't have. So, for example, this data set is about races, Formula One races, and somehow you don't have. Maybe you have races approximately every 12 days, so we cannot go less than 15 days, basically.
Yeah, makes sense. So I think this is also related to the UTG paper that I did last year, which we talk about the concept of like discretization level. So basically, the more shorter the time span, you get closer to continuous time graph or like the event-based models, and then the more coarse, you basically becomes a fully collapsed static graph at some point. So this kind of like you're kind of playing with that knob a little bit. So definitely like super interesting work, and looking forward to see any follow-up work, and maybe some of the idea here can be brought into like TGNN as well, like the idea about having a surrogate function that discales time or something like that. So are there any other questions or?
I have a question how the graph was constructed. Could you go back to the slide where you have the tables and the graph, please?
Okay.
Thank you. So because you have as nodes, you have these articles and you have the customers, and in the middle you have the transactions. I was wondering, why don't you directly connect the customers with the articles and have the transactions as kind of edges with edge attributes or something? Has somebody tried something like that, or is there a reason why you don't do it like that?
Yeah, okay. So this is like a sort of kind of question that I also had at the beginning, because I think that it's a little bit counterintuitive, not to use the transactions as node and not as an edge between articles and customers. So the reason why we did this is because usually in relational databases, when you construct the graph, you do like this. So also there is this distinction between fact tables and dimension tables. But this is a detail for relational databases. But the fact is that usually the graph is constructed in this way, and for RDL they choose this kind of this representation. So we stay consistent with respect to their work in order to be, let's say, comparable. But in principle, you can also think about constructing the graph in another way, and we are also working together with Antonio, with some students, to try to use another representation of graph, and so this is another possible direction, and we are also kind of working on it. So so far for our work, we just stayed consistent with the definition that RDL gives about the relational graph.
Yeah, makes sense. Okay, thank you.
Thank you very much.
Okay, great. If there's no more questions, we can wrap the talk here. I just want to make one final public announcement. So we have made the announcement on the Temporal Graph Learning Workshop for KDD 2025, in case you have seen it or not seen it. So you're welcome to submit like the workshop paper there. I think the RDL topic will be quite on topic, and also some people from Kumo side will be our guest speaker there. So I think there will be quite a bit of discussion on RDL this year in the workshop, I suppose. So yeah.
Thank you.
So thank you again for the excellent talk. And thanks for all the discussion. So yeah, so have a nice week, guys.
Thank you.
Thank you
Thank you
very
so
much.
much for hosting.
Thank you.
Thank
Thank you.
you.
Bye.
Bye bye.
Thank you. Bye.